Alrighty, guys, so we need to get back to truth table. So let's do a quick review before we get into solving some of them. So these people will not be able to see what I write on this. All right, just those of you who are on Zoom, to let you know, I did forget my laptop at home today, so I'm trying to teach from our desktop, and it will probably look a little bit different than what you are normally used to. Okay, so I do apologize for that. All right, so remember we had talked about how do you set up a negation truth table, right? So the idea is if you take the original proposition and whatever its truth values are going to be, the negation of that is the opposite truth value, right? So if it was originally true, a negation of it would become false. So basically, like I would say, I am running late today, which is true, right? But then if I say I am not running late today, then that would be false, right? So that's what the negation will do, is change your truth value. Then we talked about what happens if you take two propositions and combine them together using the word and. So the only situation where an and statement would be true is when both propositions are individually true, and then your and statement would be true. In any other scenario where even one of those statements is false, your combination statement, combined statement would be false. For the or, if we take two propositions again and combine them using or, then you would have the only time an or statement is false, because remember this is inclusive or, so one or the other or both of them. So as long as one of them is true, your or combined statement will be true. The only time an or statement fails is when both parts, right? Both propositions are false. So that was your not or negation, and which is your conjunction, and or, which is the disjunction. So the names that we give those kind of statements. Then we had also talked about conditional statements. That's the if then, right? If this is the premise, then this is the conclusion, right? So in that setup, the only time a conditional statement fails is when the first part is true, but the second part is false. So we're basically saying, we're talking about you meet the condition, right? You meet the premise, but you're not getting the conclusion. And we had talked about that example of if you post this picture, you lose your job or whatever. So the idea is you posted the picture. So the idea was you should be losing your job, but you didn't. So that's the only time where we would say this claim we are making is false. So that's the only situation it fails. In all other cases, you will see your conditional statement is going to be true. And then they didn't give us the biconditional. Biconditional is where it's the if and only if statement, right? So this is only true when both statements are true or both statements are false. It's going to be true, right? And the other cases where one is true, the other is false, it's going to be false. Yes.
Doesn't it say up there if the premise is false and end state is true, it's still true?
Yes. So the idea is, in that case, we are saying you didn't post the photo, but you still ended up losing your job. So in that case, we're saying the claim is not false. Because the claim is specifically saying you post the photo, you lose the job, right?
Yep.
They didn't talk about what happens if you didn't post the photo. Because there was no condition given, if you don't post it, then you get to keep the job, right? That was not the statement. So we're saying, yes, in that case, it is still going to be true.
Right.
Yeah, so we're just going about the claim is true or not. It's not about, what happens or what the consequences are. Because, we kind of start thinking that, but that's not what we're interested in. All right, very nice. So let's build up on this. And I think we had done example 4, and that's how far we made it. And I just kind of went over this quickly. Let's deep dive. I know this is going to be scary, but if you can do the hardest part first, the smaller ones will become easier. So let's start by how do you set up a truth table? And we are going with 3 propositions here. So you have A, B, and C. So all 3 statements. So you can see they started us off with A. Hold on, what's going on here? This will be very, very interesting. This. Okay, so you start out with four T's, four F's in the very first column, right, for the first proposition. Then we alternate with pairs of two, so you will do true and true. Sorry, guys, this is not placed as I would want it to be. So alternating pairs of twos now, so you will do false and false. Then we will go back and alternate with truth, so true and true. And then you will alternate again with false and false. Right, so that's how you set up the second columns in pairs of twos, and then the last one for column C, it alternates by one. So true, false. So alternate those three. Now this setup will always stay the same if you're working with three propositions, okay? So get those first three going, and then we will break each one down individually. So you can see we are talking about not A. So that means we're doing a negation on A, right? So right now you can see A is going to be all four trues and then all four falses. So reverse that order in the not A column, which means the first four are going to be false. And then, of course, the falses become true, so the last four are going to be true. Jessica and Raven on Zoom, you guys okay so far with me? Yeah, so you can unmute if you have a question, or you can put it in chat, whatever you're comfortable with. And your classmates are gonna help me keep track of the chats. If you see a chat pop up and I'm not responding, just let me know, hey, Ms. Aruka, there's a comment on the chat. All right, guys, so what do you think not B will look like now? So the negation on the B column, what will that look like? Give me the order. No, because you're negating the B column, right? So that's the second column, not the B column, so you're negating that. So if you started out with two trues, two false, two trues, two false, what will the not B, the negation of B have?
Two falses, two truths, two falses.
Oh, reverse that.
Reverse, yeah.
Yeah, because the trues become false, right, when you're doing the negation. So that actually means, since you started out with true, and then false and false, reverse that, which means the true values will become false. And then the false will of course become true. And so again, we had true and true, so those now become false and false. And then the last two were falses, so they will become true and true. Oh, well, not sure I can fix that. So you are literally just going with the opposite truth value from what the column A and column B had. Let's see if I can use my little pointer. Okay, so you will see how these first four values were trues. In the negation column, those first four values now became a false. Yes? The last four were false. So you will see you switch that to the opposite and they became true. For the B column, you had T and T, which in the negation will become F and F. Then you had F and F, which became T and T. The T and T in the original become F and F in the negation. And then the last two were false and false, which ended up becoming true and true. The negation go with the opposite. Now, when we are talking about doing not B and C, so your connecting word here is and, you're actually looking at not B, this column, and you're looking at C, because it's going to be between not B and the C column. Now, since this is an and statement, it's okay if that order is reversed, because you can see C is showing up first in our table and then the not B. If this was an if statement, I'd probably want to put them in the order of going from left to right. But since this is an and, it's okay if C goes first and not B goes. Kind of like addition, like 3 plus 5 is 8, 5 plus 3 is still 8. So it kind of works both directions. Now remember, for the and, both values have to be true for the and statement to be true. If one of my columns has a false, or the other one has a false, then my and column will have a false. So as long as both parts are true, I can put a true in there. So let's take this step by step. Starting out with column C, you can see this is a T value, but this is an F, right? So that actually tells you, since one of them was an F, this is going to be false. If we go to the second row, you can again see I have a false here and a false here, which means both are false. This guy is going to be false. Going with the third row, you have a truth value here and a true value here. So since both of them are true, your and is going to be true. So based on that idea, what do you think this guy should be? There's an F here and there's a T here. What should this value be? If one is F, the other is T. Sure. Yeah. It's going to be a false. As long as one of them is a false, it's going to be a false statement. This guy is a truth. This guy is a false. So what should your and statement have? Nope, if one of them is false, it's going to be false, right? Because this guy was an F here. And I know he's kind of out of line, but it's supposed to be in that space, right? So one of them was a false. Same thing here, right? This guy is, sorry, using the wrong. Sorry, it was a true and a false combination, which still would have been false. For the, what is this? Sixth row. This is false and this is false. So since both of them are false, of course, your and statement is also going to be false. What about this guy here? He is true and he is true. So what will your and statement have if both are true? Yeah, that's when the and statement is going to be true. Very nice. And then that brings us to the last one. You have a false statement here, a true here, and of course, since there's one false between those two, this guy will be a false statement. So that takes care of the parentheses part, right? The not B and C was in your parentheses, which is what we have just taken care of right now. So not B and C is what this column was. And then, of course, we went ahead and did the individual not A, not B. So you've done all the smaller parts. Now you want to do the entire statement together. So this is where we are saying you are taking not A, and then the parentheses part, which is that very last column we just worked on, and you are using the or connector between those two parts, which means you will be looking at the column not A, and you will be looking at this last column that we just completed, not B and C. So these are the columns that we are comparing. So you can see, so this is the or connector, right? So remember, what did we say about or? As long as one of those numbers is, values is going to be true, the or statement is going to be true. If both are false, that's the only time an or statement becomes false. So let's take a look at row 1. And this one you will see I have false over here and false over here. So since both of them are false, obviously this guy is also going to be false. Let's try and get him more in line. Okay. Row 2, you can again see this guy is false. And the last one is also false. So again, since both of them are false, this one is also going to be a false statement. Or condition, I guess you could say. Scenario. This guy is false, but this one here is true. So again, as long as one of them is true, your complex statement will be true. Row 4, both of them are false again. So since both of them are false, of course, your compound complex statement is false also. Next one, you have true here and a false here. So again, as long as one of them is true, your complex compound statement is going to be true. Row 6, again, you can see this guy is true. The one is false, but one of them is true. So again, my compound statement will be true. Row 7, you've got both of them as being true. So of course, that means the or statement is true. And the last one also has a T in there. So since you have one truth value here, E happens to be false, but because one of them is true, so step by step, you want to break this down. And I know this may seem like, why are we doing this? Especially because right now we haven't defined what A, B, and C stand for. And when we put it together, what is this statement talking about? But that does not matter at this stage because we need to know how to add and subtract, right? Before we can jump into word problems. So think of it in that sense, that we're just kind of setting the foundation right now, letting you guys get used to how to work with truth tables, remembering, how to do the negations, the and, or, if, then, those kind of things. And then we'll get into, okay, if this is what A, B, and C stood for, if this is our statement put together, what does that mean? And when do we say this argument is valid or this argument is invalid? And, a great example for that, recognizing the validity of a statement might be to think about, we see advertisements, and even though we're not in print media anymore, ads are being thrown at us everywhere, right? On social media, on TVs. We're in election year, so there's a lot of claims being made by people, right? And not just nationally, we have local elections also, regional elections also. So how do we know if a statement or a claim somebody's making, is that true or not? Right now, housing is such a big topic, right, of discussion, because we are at a shortage for housing. So you will see people talk about oh, you can get this amazing house for so much money, and we've done all these repairs and stuff, and your interest rate is whatever, but how do we know those claims are true or not? And this is kind of what this is doing. It's taking the smaller parts, breaking it down, and then saying, okay, if I put this all together, when this is true, then I know my statement's going to be true. Or one part may be true, but the other ones may be false, but I can still say it's true. So that's kind of what you're doing, is breaking it down by case. So that's exactly what's happening here. So this was where they gave us a truth table that, we were able to just break it down. But how about we create one of our own truth tables from one of these bottom ones? And again, you know what, let's deep dive, let's do this guy over it. The question is, where am I going to do this? Whiteboard. Jessica, just want to make sure you guys can see the whiteboard. This is the problem. Okay, so if we were creating, I'm not sure how this will come out to be, guys, but Okay, so we should have a column. Mhm. And I'm so sorry, this is not coming out like in line and. Just trying to figure it out. I think this will work out better. All right, so we've got A, B, C. So of course you want to start out with those first three base columns. Okay, sorry, I'm asking you this again, but Jessica and Raven, you guys can see the Excel worksheet. Yes. All right, awesome, awesome. How do we break this down? Now we know this is an if-then statement. What do you think should go into our next column after we do the A, B, and C, the first three propositions? Looking at the statement, they're saying if parentheses B or C, then parentheses A and B. So what would you put as your next column heading in the truth table? Yeah, very nice. It's going to be B or all right, very nice. And then for the next column after that? Yeah, so that's your next set of parentheses, A and B. And then of course, the last one would be your if-then statement. All right, so again, remember your traditional setup is going to be with first four values being T's. And then the last four in that column A being F's. Then for column B, we alternate in pairs of two. So you do true, true, false, false, true, true, false, false. Column C, it's every letter that alternates. So it's going to be true, false, true, false, true, false, true, false. And I'm going to give you guys a chance to work on this because I do want you to practice. So let me get those A. Oh, can I not get all of them on the same page? Too small. Sorry, guys, it's not letting me do all of them on the same page. Let's do and or right now because those are the first two columns you are working on. Try and get them on the same-ish page so you can kind of follow along and see. So I'm going to give you guys a couple minutes and go ahead and do B or C column and the A and B column. We'll do the if then at the end, but do the first two at this stage, which is B or C, A and B. And Raven and Jessica, what I'd like you to do is share your B or C, just put them in order, the T and F's, that you have and send it to me individually, not to everyone in the chat. So when you message me, just look at my name and send it to me directly. I just want to make sure you guys are on track with me on that. So what would your B or C column look like, and what would your A and B column look like? The C, you are alternating each one, so then go true, false, true, false, true, false.
Oh,
and then, go ahead and do. Yes,
So
okay,
turn
yeah,
around
just
again.
get caught up, yeah. And make sure you put your title on the top so you know which column you're looking at. Yeah, so you don't get confused with that. That kind of seems to be what I have seen people have who got through that part yet. Oh, sorry. I'm gonna try and squish between you guys, sorry. Okay. That seems to be the theme, so I'm kind of going that you guys are on the right track. Yes. No, so now you are doing the B or C column, which means, you're going to be looking at both B and the C columns and using the OR, right? So that means as long as one of them is going to be a truth value, your, B or C column will have a true. If both are false, then it's going to be false. So, let me see. Oh, Raven, I'm very sorry to hear about that. So sorry. All right, guys, let's take a look over here. So like I said, with B or C, which means these are the two columns we are looking at. And you know what, let's put them in color, so just so we know what we're working on. So if one of them is going to be true, and you can see in the first row, both of them are true, which means this guy is going to be true. Row two, one of them is true, the other one is false, which of course means this guy will be true. Third row, same thing, one of them is a truth value, so you will have true in here. Row four, both are false, and that's when the OR becomes a false, right? So this will be false. True and true, so this guy's a true. True and false, so of course a true. False and true, true. And again, you can see both false values, so this guy will be false. Yeah? And as I was walking around, most of you had the T, 3 T's, 1 F, 3 T's, 1 F, right? Alrighty, then we look at the and column. Now, and column, and again, remember for the and, as long as both of them are true, your and statement is true. In every other case, it's going to be false. So that's what we're looking for. Are both of them going to be true? And this is A and B. So would be these two columns over here. Orange. So A and B, you can see both of them are true. So this guy will be true. Both of them are true. So again, the and is going to be true. And then let's see. There's one false, 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 right? So all the remaining have a F in one or the other statement or both of them, so that's telling you all of these guys, remaining 6 conditions are all going to be false, which is again what I saw with those of you who had made it to that point, that you had the 2 T's on the top and all falses on the bottom. Okay, so we've actually done all the parts. Now we need to put the final statement in together, and this is where the if-then statement comes into play. So this would be the table we would be looking at. So again, guys, as long as the first one is true and the second one is false, that's the only time an if-then statement becomes false. In all other cases, you can see it's going to be true. So that's what we are looking for. The first one is true, but the second one is false. And that's why the order is important when you're working with the if-then statement. So, and that's why we wanted to put the B or C column first, because that's the premise, the if part. And then the A and B was the conclusion, the then part. So I did want B or C to be on the left, A and B to be on the right, so that I can follow from left to right direction. So we are looking at these 2 columns now, the very last 2. Okay, so that we can see the full statement there. All right, so you can see we are going from true to true. So that's going to be true. True to true. Again, that will be true. The first one is true, but the second one is false. Remember, this was the exception. So this is where this guy becomes a false. Both are false. So technically the if then is going to be true. First one is true, second one is false, and that's actually happening in the next 3 rows, right? True on the first one, false on the second one, which means all of these guys are going to be false. And then the last one, both of them are false. So that's actually telling us the claim itself is true, even though each individual statement is false. So there are 4 conditions where your if-then statement can be true and 4 conditions where the if-then statement can be false. And again, guys, if we knew what A, B, C stood for, then we could kind of put it together in what scenario we are looking at. But again, we're just kind of setting the stage for this right now. Question on this example over here, guys. On Zoom, did you guys have any question on this? No? Okay. I will try to save this and share it on B2L. Let's see, I think we're done with. Is there any other example in that 11 to 16 you guys would like to look at, or do you think you have a good, at least a good sense of what you need to do? Any example out of those last, well, 5, because we did number 16, but any of those you want to look at before we move on? Same question for Jessica and Raven, if there's any one of those that looks, I don't know, big, bad, scary, that you would like me to go over. Okay. So that actually brings us to the end of section 1.7, literally. So let's get into section 1.8 then. Okay, guys. So we're saying basically a logical argument is a claim that a set of premises supports a conclusion. And that's kind of what we've been doing with the and, or, if, then, negation statements. It is possible for a logical argument to have one or many premises, but there can only be one conclusion, right? Because ultimately you are reaching that one final, whatever it might be. So we're basically looking at different types of arguments here. We're going to determine the strength, the validity, or you can think of the soundness of each type of argument. So we start out with inductive and deductive arguments. So let's take a look at this guy over here. To better understand the difference between inductive and deductive arguments, we are talking about when I went to the store last week, I forgot my wallet. And I forgot it again when I went back today. I always forget my wallet when I go to the store. So We're basically saying this person is talking about how they always forget their wallet when they go to the store, right? Because they said, I went last week, forgot my wallet. I went today, forgot my wallet. So based on that, the conclusion is, I always forget my wallet when I go to the store. Alrighty. So in this case, we're saying it is helpful to precisely state its premises and conclusions. Most arguments you encounter in real world won't be stated in a precise, there's not going to be like an order, like this is the premise, this is the premise, this is the conclusion. So you would kind of have to look at the statement and kind of say, what do we think is the premise? And based on that premise, what is coming out to be as the conclusion, right? So I guess I kind of jumped the gun on that and already told you, but we'll look at it anyways. So they're saying sometimes the conclusion can be stated before the premise, and then sometimes the premises will be hidden within a bunch of rhetoric. All right, so let's take a look over here with this little example over here. I forgot my wallet when I went to the store last week, so that's a premise. I forgot my wallet when I went to the store today, so the conclusion, like I said, is I am always forgetting my wallet when I go to the store. Sadly, that's a true story with me. It has happened many, many times where I have to run to my car and I'm like, I'm in the checkout line. I'm so sorry. With the phones, I can do Apple Pay. And so I'm so used to it. But then you go to like this ancient store and they're like, oh, we don't have tap. You can't do Apple Pay. And I'm like, Walmart. So I don't shop at Walmart. You don't take Apple Pay. I'm not shopping. So yeah, I mean, it happens, right? But can we say it happens every time or it's always? Because I think that's the key word here that we're looking at. So note that both premises make a claim about a specific instance, the specific instance being last week and today when they forgot their wallet. And then the conclusion is actually saying more general, right? Because they're saying, I am doing this always. This is happening all the time. Okay, so you went from a specific to a general conclusion, right? Your instances were specific, but your conclusion is general. All right, let's look at this other guy over here. Henry must know CPR because he is a nurse and all nurses know CPR. So what would be our premise here? So the premise actually would be all nurses know CPR. Henry is a nurse, so the conclusion is Henry should know CPR, right? So you will see how differently this statement was worded because your conclusion is actually right at the beginning. It says Henry must know CPR. And then they said, why do they think that, right? What's the premise? Because he's a nurse and all nurses should know CPR, right? So that's kind of your statement in English. So in this case, we're basically saying the premise is actually a general statement because we are saying all nurses must know, right? So we're generalizing and saying anybody which is kind of the expectation, right? If somebody tells you they are a nurse, you're automatically going to say, oh, you know this or you know that, couple of things, one of them being CPR. So you're actually starting out with a general premise and saying all nurses know CPR. And then the conclusion is specific to Henry because we are saying Henry, who is a nurse, should know CPR, right? So you went from a general argument to a specific conclusion, whereas in the wallet example, that order was reversed, right? Because there were two specific instances where we forgot the wallet, but we generalized and said, oh, we forget our wallet every time we go to the store. So that's actually where this idea of inductive and deductive argument comes from. I love this graphic because I think it kind of helps you visualize how you would want to look at the two arguments over here. So the sorry, am I reading that incorrectly? No, I am reading that correctly. Yeah. So the first example with the wallet and the store, since we went from a specific to a general conclusion, we would say that is an inductive argument. In the CPR and nurse and Henry example, since we went from a general premise to a specific conclusion, we would say that is a deductive argument because you're deducing, right? We are saying you're going from a general theory to a very specific result. So in general, we are saying inductive argument is a collection of specific examples as its premises and uses those specific examples to create a generalization. With a deductive argument, it's a collection of general statements. So you're going from general statements as the premises and then coming to a specific conclusion. This may be not a happy statement. But, as a math instructor, you can imagine a lot of times I hear students say, I've never done well in math. I've always been bad at math. And so I think that is their way of saying, I may do bad in your class, right? Because, so what's happening there? We're going from a general statement, right? Because we're saying, I've never done well at math. And I'm guessing that means high school or maybe a previous college level class. And so they're taking that general argument and they're saying, so the conclusion is I'm probably not going to do well in your class, right? So we're going from generalization to specific, which would then be deductive, right? Because we're saying I've never done well in this, I'm never going to do well going forward. And that's kind of where that deductive comes. But inductive is saying, I did this today, I did this yesterday, so I always do this, right? And that's kind of what you guys need to kind of differentiate between the two arguments for. So let's take a look, and you can kind of read some of the more detailed stuff they have in those paragraphs. So let's take a look at this guy, number 184. Rewrite the following arguments in a precise premise, conclusion form, and then we'll talk about if the argument is inductive or deductive. So part A is saying a number is prime if it is only divisible by itself and 1. Since the number 13 is only divisible by itself and 1, 13 must be prime. So which parts are the premise and which part is the conclusion? A number is prime if and only, a number is prime if it is only divisible by itself and 1, which we know is the definition of a prime number. They are saying since the number 13 is only divisible by itself and 1, 13 must be prime. If it helps, you can try and identify what you think is the conclusion first. In that statement, A, what do you think is the conclusion that we're making? 13 must be prime. Very good. So that means what is going to be the premise, the two arguments that are leading to that conclusion? Basically, the definition of a prime number, right? A number is prime if it is only divisible by itself and 1. And then we're saying the number 13 is only divisible by itself and 1. Alrighty. So hang on to that. Part B is saying Juan's dog, Goober, is having puppies. All 3 of Goober's previous litters have had 5 puppies. So Goober is bound to have 5 puppies in this litter as well. So again, what would be the premises? What would be the conclusion? So Juan's dog Goober is having puppies. All 3 of Goober's previous litters have had 5 puppies. So Goober is bound to have 5 puppies in this litter as well. What do you think is the conclusion here? Goober is going to have 5 puppies in this litter. Okay, so what would make the premise? Premise. So previous litters had 5 puppies and the other one? Well, first part, right? Because Goober has to be pregnant to have puppies. So, right? So we know Goober is having puppies. All right, so let's see if we did that correct. Oh, I guess we didn't talk about deductive, inductive. Oh, well, we're getting there. So yeah, part A, we talked about if a number is divisible by itself and 1, then that number is prime. So that was a premise. We did good on that. The second premise was 13 is divisible by itself and 1. So we knew that. And yeah, your conclusion was 13 is prime. So you will see we actually went from generalization to specific, right? Because we're talking about all prime numbers. And then we're saying, okay, conclusion 13 is prime. So since you went from general to specific, as you can see, that makes it that deductive argument again. In the Goober puppy example, So I can get that on the same page. Okay, so here we had basically said the current litter, the babies, puppies Goober has this time will have 5 puppies. So we did well on that conclusion. And then you can see, yeah, Goober having puppies and the last 3 litters having 5 puppies was the premise, right? The argument we based on. So this is actually going from specific instance to generalization because we're saying, okay, 1, she's pregnant. 2, the last 3 of her litters were with 5 babies each, which is a generalization, right? Because how do we know that is going to happen this time? But we're just saying because the last 3 did that, we're saying this time it's going to be the same result as well. So you're going from specific instances, specific cases, and you're making a general conclusion in this case. So of course, this becomes an inductive argument. So going from specific to general, going from general to specific. All right, now let's talk about the strength of an argument. So inductive arguments cannot be proven, and that is again because you are going from a specific case to a general. So let's go back to the wallet and the store. Last week we didn't have the wallet. Today we don't have the wallet. So we are saying every time or always, I think was the word they used. I always forget my wallet when I go to the store. Now, can that be proven? Because there might be some instances where you're lucky and you're like, oh, I better take my wallet because what if they don't have that tap thing, like in my case, right? So sometimes especially if I have pockets in my outfit, I will throw my wallet in there. So at least I can be like, yeah, don't have to run back to the car. But there's no way to prove that I'm always going to forget the wallet or this person is always going to forget their wallet, right? So you cannot prove an inductive argument. So the best thing we can do is evaluate the strength of the argument based on the evidence. So a strong inductive argument is one that is well supported by its premises, while a weak inductive argument would be the one where the premises do a poor job of supporting that conclusion. So the strength of an inductive argument is subjective because, one person might see it as a strong argument. Another may say, no, that argument is not very strong. It's a pretty weak basis there. So the strength and truth of an argument are not necessarily related. It is still possible to have a weak argument that might be true or a strong argument that might be false. So let's take a look at this guy over here. James Franco, Jodie Foster, Jennifer Lawrence, and Jack Nicholson have all won Academy Awards for acting. I actually did not know James Franco had an Academy Award. Actors whose names start with J are bound to win an Academy Award. So we're talking about the strength of an argument here, yes? How would you define the strength of this argument? James Franco, Jodie Foster, Jennifer Lawrence, Jack Nicholson, 4 people whose names begin with J have had Academy Awards. So we're saying any actor whose name starts with a J is bound to win an Academy. So in your opinion, because we did say this is subjective, would we say this is a strong argument or would we say, I'm sure there are many other actors with names starting with J. I mean, there's a bunch of other Jennifer actresses, right, who have not won Academy Awards as far as I know. So we could kind of say, be nice if everybody who had a name starting with J won an Academy Award, but we know that's not true. So yeah, obviously this is inductive because we're going from a specific case to a generalization. And like we said, many J-named actors have not won an Academy Award, so the argument there was pretty weak. All right, deductive arguments, on the other hand, can be proven and their validities and soundness can be evaluated. Because remember, this is where you are going from generalized premises to specific, right? All nurses know CPR. Henry is a nurse, so Henry should know CPR. So yeah, we're able to follow that track and we can say, yes, this argument can be true or false, or is it valid or not valid? Can be proven for their validity and soundness. The validity of an argument is based on whether the conclusion follows logically from the premises. The soundness is based on not the premise is true. So validity is, does it have a logical path, following from the premises to the conclusion? Does it follow like a logical path? Soundness is saying, are your premises true or not? So based on that. So the last one here is important to remember, bless you. An argument cannot be sound if it is not valid. So if there's no logical transition happening, you cannot say if an argument is going to be sound if it's not valid to begin with. So let's take a look at something. And they're saying even if the premises are reasonable, if it's not valid, it's not sound. So they're asking us to actually use Venn diagrams to, or sets to come up with the validity and soundness here. So we're saying, okay, one way to determine a deductive argument is valid is you can illustrate using sets and see if the conclusion logically follows the premises. So use a set diagram to determine whether the argument is valid. If the argument is valid, then we will talk about the soundness. So all cats are mammals. A tiger is a cat, so a tiger is a mammal. Okay, first, what is the conclusion in this statement? Part A.
Tiger is a mammal.
Tiger is a mammal, very good. What would be the premise in that statement?
Cats are mammals.
And the other one?
Yeah.
Very good. Give me a straight-ish line there. Okay. So how are we going to do Venn diagrams based on those two premises? So Venn diagrams, remember where we have those circles put it together? Okay. So if we had to do a Venn diagram, what would our two circles comprise?
Now, cat, tiger. So 3 circles.
No, two circles only. Because a tiger is a type of cat, so you don't really need a circle for a tiger. Tiger is gonna be our point where we need to decide where we will place him, or they, it, I don't know. One of those prepositions for a tiger. So the two circles need to be mammals and cats actually. Because there are other types of mammals, right, that are not cats. Oh, this will be interesting trying to draw the shape. There you are. All right, so our rectangle-ish. And then our circle. And to do that on the upper half of that rectangle, not the bottom half. So since we are saying all cats are mammals, do we create like a overlapping circle? Or does one go into the other? Because if all cats are mammals, then think about mammals as a larger species, right? The larger circle, and then cats is gonna be a smaller part of it. So you're actually going to put cats on the inside. We are saying all cats are mammals, so this guy should be cats. This would be mammals. Or at least that's kind of my thinking here. We may see the solution may have something completely different. So if we're saying a tiger is a cat, where would we put the little dot or an X or whatever for a tiger? Would we put it in the mammal circle? Would we put it in the cat circle? Cat circle. So our little tiger dude is gonna go in there. So then does that follow that, can we say a tiger is a mammal then, based on the Venn diagram? Yeah. I almost was worried that I did this incorrectly and I'm gonna like lead you down the wrong path. But yeah, And remember, we had talked about the qualified statements where you use words like all, none, no, or some. And so in that was the main reason why we knew one circle needed to go inside of the other one, because we're saying, all of cats are part of the mammal group. So that's why you put one inside of the other. If there was saying some, then that's where the overlap would happen between the two circles. None would be where they would be completely separate from each other. And you will actually, we will lead to that here in a minute. Everybody okay on part A? Yeah, all right, let's look at part B over here. Let me just save this little.
So in that case, if they asked you what the outside was, it would be the universe, right?
That would be, I guess, all animals? Would be the rectangle? I mean, you could almost argue it could be all living creatures. I don't know. I guess we're mammals, so we could be in there technically. So yeah. All right, very nice. All water bottles are plastic. This is a water bottle, so it must be plastic. So what's our conclusion here?
This water bottle is plastic.
Okay. I'm sorry, guys, that was supposed to be a straight line, but you get the idea. I am really missing my laptop. I'm not gonna lie. I was gonna actually stay back in the student comments and work. But obviously that's not gonna happen. I'm gonna have to go home so I can get caught up with all of your homework and put it all there. So yeah, this is a mess. But will teach me a lesson to not sleep 10 minutes extra next time. All right, what are the premises then if this is a water bottle, or sorry, this water bottle is plastic is the conclusion? Very good. And the second one? This is a water bottle. All righty, very good. So then the question is, what would our Venn diagram look like? Okay. Let's see if we can. So plastic is the larger circle. Now, so my question is, do we put the entire water bottle circle inside of plastic like we did with cats?
No.
Going to be the opposite. So I can see that wheel turning. Go ahead.
Right.
Why? Yeah, because are all water bottles plastic? I mean, look at your own, look at yours. Corey, I cannot tell what your material is. I'm sure there's aluminum somewhere on the inside. See, we've just proven it in like 2 water bottles in class. I know this guy is fully plastic. There is like no. That's true. Okay, that's my version of a circle. Do not be making fun of any of my writing or drawing. So some water bottles are plastic, right? So we could put some in there, but if they are saying all water bottles are plastic, then I'm almost thinking, because it's the same kind of statement as the A, are we supposed to put that circle inside? All water bottles are plastic.
Are we going off the statement?
We
on
are.
What is true?
Statement.
Then I think it would be.
Because that's what I'm thinking, if they're saying all water bottles. Now, this is a water bottle. Okay, so if this is a water bottle, it has to be plastic. Because that's where we're putting that circle, so in that sense. Yep, look at that.
Make Portland all water bottles are plastic.
And I have been there for 2 hours to eat lunch and then.
Do you see any metal water bottles?
That was 8 years ago. I didn't even know what I was doing that day. I do know I had some really good pho though, so. Ask me about food and I'll remember. Any other details? No. So you can see that's kind of, because they said all water bottles are plastic, right? So we had to put the water bottle circle inside, and then you had asked me, do we do this on what's true, or do we do this on what the statement is saying, and you actually do it on the statement. So we do know technically that is incorrect, but the idea is if this is the premise, this is the premise, and this is the conclusion, is there a logical path that it follows? And in this case, we would say, yeah, since all water bottles are plastic, we take the bigger circle of plastic, put the water bottles in that, and then since the second premise said, this is a water bottle, it had to go inside the water bottle circle. So by that premise, your conclusion saying this water bottle's gotta be plastic, it follows through on that argument. And then you will see here, we're saying this would also be a valid argument, like our first one with cats and mammals, because we were able to show logically that this follows. So in practical, and I think that's where the confusion and the fight comes, because we know this should not be true. Not all water bottles should be plastic. But again, that's not what we are arguing here. We are arguing this statement this person made. Are we able to logically follow that and say, is this argument valid? We're not talking about if it's true or not. That comes the second part. Right now, we're just saying, is the argument valid? And you will see here, yeah, so you will see right here, but the argument, what is that? The second statement in that paragraph, I guess, for Zoom people. Use my little pointer. So you will see right here, we're saying, but the argument is not sound because the premise is that all water bottles are plastic is not true. There are glass water bottles, metal like you guys have. So we know the argument is valid. It's just not sound because it's not true. So I think that's where we need to like understand the difference between them. Logically, yes, we could follow that path, but when it comes to soundness, that's where we're saying because it's not true, it fails as a valid, as a strong argument, right? Okay, valid but not sound. That's what this argument is. All right, and this guy was option B. Let's clear this guy up. And again, if anyone on Zoom has a question, just let me know. All firefighters know CPR. We're kind of going back to a similar example we did before. So all firefighters know CPR. Jill knows CPR, so Jill must be a firefighter. Now, again, we can do the strength soundness argument on this, but let's talk about the logical step here. So we're saying all firefighters know CPR. So how would you set up your Venn diagram again for this guy? So all firefighters know CPR. Jill knows CPR, so Jill must be a firefighter. So what would our two circles be for this example? No, Jill is the dot. Jill is the little person or place or thing that we put inside the circle. So the circle will not be Jill. So it's got to be firefighters, and what's the other one? CPR. So which one? And this is same statement, right? All encompassing. So what's the outer circle going to be? The bigger circle. CPR. So that means firefighters will go inside the CPR circle? Because we're saying all firefighters know CPR? Are you a firefighter in training or you are full firefighter? So you know this. So we'll ask you about whether Jill can be a firefighter or not. So where would we place Jill? Do we place Jill inside the firefighter circle? Do we place Jill just inside the CPR circle? Because that's what they're telling us, right? The conclusion is Jill is a firefighter. Oh, I guess I didn't ask you guys that. But yeah, the conclusion is Jill is a firefighter, but the premises are they know CPR and all firefighters. So we know Jill knows CPR, which means technically they should go inside the CPR circle, right? They cannot go inside the firefighter circle because there's no premise or anything telling us. So in this case, can we say this is a valid argument? No. Because Jill cannot be placed inside of the, that's interesting how they did that. If you can see kind of under my writing, they're actually placing Jill at kind of the cross section. It looks like of where the two circles are, right? Not quite as farther out like I did. So this one is saying, yes, firefighters would be a subset of people who know CPR, so we put the firefighter inside of the CPR circle. We know that Jill is a member who knows CPR, so definitely goes into the CPR, but we don't have enough information about them being a firefighter. Okay, so since we cannot group Jill, must be part of, since we cannot determine which group Jill must be a part of, yeah, the argument is invalid. I almost read that as valid and I was like, no, that's not right. So yeah, since we cannot place them inside of the firefighter circle, there is not a logical path that you can follow. And in this case, we would say the argument is not valid. And remember what we said before, if it's not valid, it cannot be sound, right? So this is where we're saying there's no soundness on this argument either. So you can kind of contrast with the two examples we did, right? Our little tiger went inside the cat circle, so we were able to follow that path along. And then with our water bottle, also we were able to follow the path along and take it to plastic bottles. So those arguments followed. But with Jill, like we said, we don't know if we can place her or them inside of the firefighter circle. So that's where your argument is losing its validity. All right, part D is talking about none of my friends like dancing. Kai doesn't like dancing, therefore Kai is my friend. What? None of my friends like dancing. Kai doesn't like dancing. Therefore Kai is my friend. How would we set that up? In the Venn diagrams? Okay, so dancing and friends would be the two circles, and then how would you set them up? Now, there's no all in this case, right? So one cannot go inside of the other like we did for the first three examples. So how would you draw the Venn diagrams? None of my friends like dancing.
There kind of is an all.
Yeah.
None implies that all of his friends do not like dancing.
Okay. And then,
So I would put
Friends like dancing.
people who don't like dancing and then friends within,
inside of that,
and then just like the one before it, it would be Kai would be on the edge of doesn't like dancing and people who are friends.
okay, let's try that. I have not tried it that way, so let's try that. So this is what you're basically saying. And then what's the outer circle then?
People who don't like dancing.
Okay.
Wouldn't it be two big circles with the in-between circle because they're all friends? But there's some that are dancers and the other that is not, but they're all friends in the end, so they would meet in the middle.
So you are saying two separate circles
Well, overlapping.
or overlapping? Okay, so let me use another. Kind of don't have space here. Okay, we're gonna squish it, Nani. You'll get me. You guys are awesome. Oval is a circle, type of, not really,
Close enough.
but you guys get the idea, yes? So this is what you're saying. So one of them would be no dancing, the other one would be friends. Okay,
Well, no, they're all friends, so no dancing friends versus just friends that don't dance. So
How do we know that Kai is a friend? That's
so these are friends who dance. And these are friends who don't dance?
something like that. I'm not,
What if it was,
Not sure that would
His
work
friends
out.
on one side, people who don't like dancing on the other, and then.
Say that one more time?
So it'd be Kai on one side and.
No, chi is a dot. So chi is not a circle. So are we going back to friends as one circle and people who don't like to dance as other circle? You're onto something there. All right, so before we get to, sorry, Lauren's argument, let's see what Samuel and Anna had. Okay, so if we did Samuel's where the bigger circle is no dancing, friends is a smaller circle inside of that, where would you place Kai?
People who dance.
Yeah, because again, we don't know. Because they're not saying Kai is this person's friend. They're just saying because Kai does not like dancing, there's a good chance Kai can be my friend, right? So Kai is my friend. But there's no conclusive premise, or I guess I should say, there's really no premise that is telling us if Kai is their friend or not. Okay. And then if we did the circle on the top where Anna said there are friends who like to dance, friends who, that was supposed to be an N, friends not dancing, but it looks like a W, sorry. I guess friends without dancing, however you want to look at it. Where would we place Kai in that? Because again, we don't know if Kai is a friend. But then we didn't describe a circle that was only for non-dancing. It's friends who dance and friends who don't dance. And see, this is where breaking it down helps, right? Because you were thinking, I think this should work, but then we actually break it down like, oh, actually, no. Because you know what happens is, think about it this way. If these are your friends who like dancing, then technically anybody outside of that should be people who do not like dance, or your friends who do not like. So you don't really need to create a second circle for them, because you know, that's kind of what we talked about in those set theory, right?
Yeah.
Oh my God, what was that word? It is, I'm having a brain fart here. Sorry. All right, so let's go back to Lauren's argument. So Lauren, what are your two circles again? And are you overlapping them one inside the other? Completely separate, no overlap. Okay, so no overlap at all. So the first circle was people who like to dance or don't like to dance. Okay, so these are people who like to dance. And then the second circle?
Friends, though, all of my friends do not like dancing. Kind of sense.
No, you cannot really change it like that, Samuel.
It's just the
I know in
negations.
English it seems to make sense, but you cannot really replace all with none just like that.
So none of his friends like dancing. That means
Not even.
0 of the people that are friends with him like dancing. That means all of his friends do not like dancing. It's just more and more negations on top of each other.
Yep, pretty much. All right, let's take a look at what? So you were almost there. Because you did have the people who like to dance, which I know you cannot see over the writing. But your second circle did not have to be specifically friends who do not like dancing. Kind of like I was telling Anna here, right? So if this is our circle, and I'm gonna try and get mine squished in there somehow. Okay, so if we are saying this circle on the left with my D is about dancing, then anybody who's outside of it technically is not into dancing. So you don't really need to create a second circle specifically for non-dancing. So you can just do the second circle like we have here as just my friends, right? And so basically the idea is if whoever is um, so since this circle does not even touch or overlap with the dancing circle, that automatically means anybody who's outside of the dancing circle is not a dancer. They don't enjoy dancing. So you didn't need to have specific to friends not dancing. You can just say, these are people who are my friends. And since it's, like I said, outside of the dancing circle, that automatically means none of them like to dance. So this is where we needed to be careful about, do we need to have one inside the other circle? Do we need to have an overlap, or do we need to be separate? And that's actually where the quantifier none comes into play, because when we say none, even though, yes, what you are saying in English makes sense, because if you are my friend, you do not like dance. So that kind of does encompass all my friends do not like dancing. But when it comes to logical breakdown, you do have to think of none as being a separate word from all. And so that tells you that it's actually going to be disjoint sets, your two circles are going to be separate with no overlap. And then you can see how we are placing Kai. Kai could be my friend, but there's nothing to tell us that Kai is my friend or not. We just know Kai does not like to dance, which means Kai can be here, right? Kai can be inside my circle of friends, or Kai can be, like they have it on the border. So since we do not know where we can place Kai, there is no logical path that you can follow, which makes this a not valid argument or an invalid argument. And that means it's not going to be sound either. Okay? So those quantifying words are very, very crucial to understand, because they actually kind of give you a hint as to where your Venn diagram is going to be at, what it's going to look like. Yes.
So if you don't know, like, exactly where the answer is, it's a non-logical statement.
If you cannot follow the path the statement is making, because then technically I should have been able to put Kai inside my friend circle. But there is nothing that's telling me that Kai is my friend. All we know is Kai does not like dancing. So, it's a person you know, but we don't know if they really are friends or not. So that's kind of where the argument is failing. I mean, if everybody who did not like dancing became my friends, there'd be millions of people.
Yeah.
In that circle, right? But not necessarily everybody's gonna be our friend. They're just somebody we know.
Yeah.
So that's kind of where the argument is failing. All right, very nice. Any other questions in that? All right, let's save that. And then does that bring us to the last one? Yes, it does. Some young adults make minimum wage. Tara is a young adult, therefore Tara makes minimum wage. So confusion in this statement. All right, very good. So of course, the premise would be young adults, some young adults make minimum wage. Tara is a young adult, so therefore Tara makes minimum wage. All right, so what does our Venn diagram look like here? And what would those two circles represent? And Tara again is the dot, right? Where we put Tara at. So Tara is not a circle. Tara? Now in British English, we say if it's a proper noun, you can't pronounce it anyhow. Which is not the rule in American English. So a lot of times people will call my first name as Miha, and used to drive my roommate in college nuts, because she's like, why do you not correct people? It's Meha. It's not Miha, but you see M-E and you go with the me path. And so I never correct, because I was like, well, in British English, you can technically pronounce any proper noun as the way you see it, the way it's spelled, and would drive her crazy. So we literally had arguments on that. So now I start correcting people. I'm like, okay, she'll get upset if she hears about it. So yeah, Tara or Tara, whichever one you think sounds better. So what are my two circles? Very nice. Yes. Young adults and minimum wage. Now, what would the circles look like? One inside the other, separate like we did in the previous example, or overlapping? overlapping, and that's the keyword some. So when you see some, because we're saying some means they may make minimum wage, they may not make minimum wage, right? So that means there can be a little group which will be overlapping. So yeah, we do need to make overlapping circles. Let's go through this guy so we don't confuse ourselves, and then we need one more circle in here. So let's see, minimum wage, young adult, and where would Tara go? Some young adults make minimum wage. So you can see if you are a young adult, you fall into the YA circle. If you make minimum wage, you fall into the MW. And then since we're saying some, you can belong to both groups, right? So that's where that overlapping is coming from. They're telling us Tara is a young adult. So where can we technically place Tara? Tara, sorry. The young adult circle, but does that necessarily mean that we have enough information to place them into the overlap region? Because Tara is a young adult, so technically, even if I place Tara here, I satisfy that premise, don't I? But then, yes, I could be placing Tara in here, or I think your textbook does it on a overlap. I guess actually the two overlap should be between the two. So there's multiple places where Tara can be placed. And so I think that is where I would say the argument fails. Let's see what the. Sorry, I know the writing is kind of on top of that. But yeah, like I said, there are multiple places where Tara can be placed. The second premise tells us to put Tara in the young adult set, but it doesn't tell us if we can put her in the minimum wage circle or not. So as you can see, this would again be a invalid argument, and if it's invalid, it's not going to be a sound argument. So you've seen a couple of different examples with they're valid because logically we were able to follow that path. And then some of them are invalid just because the path did not make sense, or there were multiple places where the person or item could have been placed. And so it fails in that context. So you will see, yeah, so they sometimes give you examples in this form here, where they're giving you the premise, conclusion. So, you know, it kind of sets it out nicely for us. I was hoping to look at. Yeah, or like examples 11 and 12, where they're just giving you the statement like we saw, and then you have to come up with what's the conclusion, what's the premise, what's the premise. So it can be shown either or. So just questions as we've kind of gone through this idea of inductive, deductive arguments, validity, and soundness of an argument. Now, since I'm not trying to scare you away, we are not going to be doing truth tables based validity. Because you can do a truth table, you know, take an argument, set it up in our, you know, based on, is it two statements, is it three statements, you know, create our truth table with two propositions or three propositions. And then for an argument to be valid, all rows have to be true in the final column. If all 4 rows or 8 rows, depending on how many arguments you had, if that final column for the final statement, if all of them are true, every case, then you say an argument is valid. Because we are saying no matter if one part was true or one part was false initially, you know, for each individual proposition, but if the final argument is true in all 8 cases or all 4 cases, then we're saying this is always going to be true no matter what. Kind of like with cats and mammals and tiger, right? Because a tiger is always going to be categorized as a cat. A cat is always going to be a mammal. So it doesn't matter which tiger you're looking at, a Siberian tiger, a Bengal tiger, I don't know, fictional tiger. they're all gonna be tigers, which means they're all gonna be cats, which means they're all going to be mammoths. So that argument will never fail. Okay, so like I said, I don't wanna scare you, so we're not gonna be doing any more truth tables. Your truth tables are what you saw in 1.7, and then truth table for, yes, I didn't really show you a biconditional truth table, did I? Let's just do- This guy over here, number 6. So this is for a biconditional statement, and you can see we know it's biconditional because the arrow is facing both ways, right? It's a two-headed arrow. So remember, this is where you have true and true when both your statements have the same truth values, if both are true or both are false. If it's alternate, one is true, one is false, it's going to be false. That's your biconditional. It's not that problem for you, so just copy my answers and we'll get on. But I do include other examples. You can see we've taken each one of those symbols. So this is or, and, conditional, so going one direction, and then this is of course biconditional. And then I've included a couple other ones. Let's do number 9, part A, so you can kind of see just how it would work with a negation here. So again, you're doing negation on Q, so you're looking at this column here and doing a negation. So remember, negation is basically where you go with the opposite. So if it's true, this guy will become false. If this is false, this will become true. If it's true, it becomes false, and if it's false, it becomes true. So that's your, and again, you can submit it each stage so you can see. If you're wrong at that, go ahead and pick a new problem, right? No reason to go ahead and do the whole thing and then come back, unless you want to practice. All right, so we got that. Now you are looking at biconditional between the not Q column. So that will be taking this column with the first P column. So since this is a double-headed arrow, same thing, right? Both of them have to be true or both of them have to be false. So let's see, we have, you have true over here, but this guy is false, so this guy will actually be false. We have true over here, this guy is true, so this is true. This guy is false, this guy is false, so again, it becomes true. First one is false, second one is true, so that will become a false. And you can see how a biconditional statement. I may actually finish this before I leave because I don't even have time for that. So I'll go ahead and open up this homework since this is fresh in your mind if you wanted to work on this at the same time as you do 1.7. But all right, people, we are officially done with chapter 1. Whew, finally, after 4 weeks of talking about chapter 1. So we will be going into calculation. So from next class, if you will please start bringing calculators with you. Now, remember, you want to use your cell phone calculators, that's fine, but then on the day of the exam, you don't get to use it. So I would like you to be used to a calculator that you can use on the day of the exam. So a handheld calculator is your best option. So if you have one, if not, I will see if the department has some spare ones and I'll try to bring them with us, okay? All right, have a great weekend, everyone. Be safe and I'll see you on Tuesday. Thank you, everyone on Zoom. Let me know if you have any questions. I will see you on Tuesday. Bye, guys.